So there's been a lot of code on all the presentations today, and I'm feeling a little out of sorts because I have very little code in this presentation. I'm going to talk about techniques rather than code. Sean was my saving idea of the day, or this week, because he had not that much code in his presentation. But anyway, we're going to talk about hardening the standard library. And I should point out that many of these techniques are not specific to the standard library, and in fact, can be applied to almost any other library. But we'll start with about me, because everything's always about me. I have been contributing to LLVM for about 8 years, and libc++ for 6 or 7, and I am currently the code owner, which is like the person who is responsible for libc++. libc++ is the standard library implementation that ships with Clang and LLVM. I'm also the chairman of the library working group. And I have been the chairman for about 4.5 years. I've been involved in Boost since 2001. My goodness, that's coming up on 20 years. That's pretty scary. Various contact information is here. If you have questions, that's fine. If you have questions during the presentation, feel free to stick your hand up. And if it's a quick question, I will try to answer it. If it's an involved question, we'll wait till the end of the presentation. Okay, let's get started. What is libc++? Well, I really already answered that. It's an implementation of the standard C++ library. There are several of them in existence. There is libstd.c++, which ships with GCC. There is an unnamed library that Microsoft ships. It doesn't have a fancy abbreviation. It's just the Microsoft standard library implementation. And there is libc++, which goes with Clang, and there are a couple others. There are several internal companies that have their own internal implementations. But anyway, it contains things like vector and string and so on. And motivation for this talk, why do we care about hardening the standard library? I mean, I care a lot just for professional pride. I mean, I want to do the best possible job I can. But other than that, why do we care? Pretty much every C++ program depends in some way on the standard library, uses facilities from the standard library. When you think of your program, it has a dependency on a bunch of things. It has dependency on OS facilities. It has dependency on the standard library. It might depend on other third-party libraries you use, other libraries that you've written. But the standard library tends to be at the bottom, and it tends to be part of everybody's dependency graph. If there's a bug in the standard library, it could affect hundreds or thousands, or in some cases, millions of people. And as much as it pains me to admit it, I'm not perfect. Sorry. Code in libc++, we have bugs. We get bug reports on a fairly regular basis. It's unfortunate, but there we go. Anyway, it's important to everybody who uses to write C++ code or uses code written in C++, applications written in C++, that the standard library be performant and correct. Okay, so what are some of the things that we can do? Here's a list, and I'll talk about most of these. Let's talk about testing. Testing is something that's near and dear to my heart. I really, really like tests. We'll talk about warnings, compiler warnings. We'll talk about checking preconditions. We can talk about different kinds of analysis, program analysis, static analysis, and dynamic analysis. We'll talk about other testing facilities like fuzzing and so on. And I will go into details on many of these throughout the talk. But these are the kind of things that we can do, that we actually, I shouldn't say can do, that we actually do in libc++. So let's dive into these. First off, it's really hard to believe that there are software packages out there today that people develop that don't actually have a test suite. But I run into them now and then. libc++ is not actually one of them. libc++ has a fairly extensive test suite. It's somewhere in the neighborhood of 6,000 tests. I consider that to be a good start. It would make me happier if it was twice as big. The libc++ test suite is used not just by libc++, interestingly enough. Other standard library vendors have told me that they run the libc++ test suite against their standard library implementations and have found bugs, which makes me happy. And occasionally the people from Microsoft or the people from GCC will suggest improvements to the libc++ test suite, which also makes me happy because more testing makes all of our libraries better, and it means that your code works better. Basically, the goal for the libc++ test suite, excuse me, I seem to be blowing into this microphone. The goal for the libc++ test suite is to express all the requirements that are listed in the standard as tests and check every single one of them. Every time we get a bug report, a new test shows up in the test suite, check it, testing the bug. I am not really a diehard test-driven development fan. I'm not really fond of the incremental development strategy, which is write a test, write just enough code to get that test to pass, refactor, check stuff in, repeat. But when it comes to bug reports, I am all over that. First thing I do when I get a bug report is I write a test and watch it fail. Because if I can't write a test to generate the failure, how do I know if I fixed it? Write a test, watch it fail, check the test in. Excuse me, don't check the test in. Fix the bug. Run the test again. Watch it pass. Run all the other tests to make sure I didn't break anything else. And then look for other things to fix. I have an example. I received a bug report, about 6 months ago. The bug report was multimap clear, the clear call for multimap, is not no except. I said, that's odd. Look in my copy of the standard. There it is, plain of day, no except. Go look in the map header in libc++. It's not marked no except. Oh, this is going to be an easy fix. But the question is, why didn't my test suite catch this? So I go looking through the tests, and I go find the tests for multimap clear, and there's no test there that says, static assert that this call is no except. Well, dang. Okay, add that test. Run it. Watch it fail. Okay, I'm a happy camper. And I thought about it for a little while. Let's go look at the test for map. There's no static assert there. Add that. Set? Nope. Multi-set? No, not there too. Got to add that one there too. Unordered map? Unordered set? Unordered multi-map? Unordered multi-set? Nope, 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 no tests anywhere there. How about vector? How about vector bool? No, no. How about list? No. How about forward list? No, no tests there either. How about deck? I can't find any tests for the clear call for deck. Not just testing to see if it's no except. There's no tests at all. So I sit down and write tests for deck's clear method, including a test to see if it's marked as no except. Fine, get all those tests, run them. The only one that fails is the one for multimap, which was the original bug report. Go open up the map header, type NOEXCEPT. Save, run the tests again, now they all pass. So simple bug report, really simple bug fix, 9 updated tests, 4 new tests that were missing, and then make a note to myself that I should probably check the rest of the members in the containers that it should be marked no except to see if we have tests for those. I don't know about you guys, but I have a list of tasks which are, when I'm avoiding other work, these are things I can do. You know, I really don't want to work on whatever at the moment. You know, I don't want to work on template argument deduction guides for tuple. Oh no, those are not fun. I'll go write tests against the containers. But anyway, just I make a joke about when you're writing tests, it's a great time to let your OCD run rampant, okay? But you have to be careful because it's really easy to go so far over the top, it's not even funny. So there's a balance to be struck there, and each person's balance is a little different. Mine tends to be on the order of excessive. Another example is when I check in new code to libc++. It tends to be about 90% tests by lines of code. When I implemented span, it was 600 lines of code and 6,000 lines of tests. When I implemented the first part of the calendar support for Chrono for C++, 20,000 lines of code, 10,000 lines of tests. The people I work with are not really happy with me when I have patches like that. They would much prefer smaller ones. But still, it makes me very confident in the code I've written, that I know that it does most everything very well. By the way, if people are interested in contributing to libc++, writing tests is a great way to get familiar with the code base. Anybody want to contribute tests, come and talk to me. I will be happy to talk to you about that. Anyway, testing. We also have a build bot that generates coverage metrics from the test suite. Basically, runs the entire test suite, gathers up, and gives you code coverage report to see what parts of the code in libc++ are exercised by the test suite. And every now and then, again, when I'm avoiding something I'd rather not be doing, I'll go look at that report and say, oh, look, this call over here does not get called by the test suite. And sometimes it's very reasonable. I mean, we have an internal call-in vector that checks all the vectors invariants. And during the testing run, the false path of the invariance checker is never taken, which is good. We never generate an invalid vector. But so I have no intention of getting to 100% on code coverage, but I sure want to find out if there are any public calls that are never tested. Anyway, on to warnings, compiler warnings. So there's lots of compilers, warnings out there. We have a lot of people using different compilers with libc++, and in particular, we have people who include our headers and use them with different compilers and different versions of the compilers and different warning levels. Some people don't care at all about warnings. Other people run with W-error, W-all, W-extra. And we want to support these people. Okay, and anyway, the problem is that basically to support all these people, we basically have to get to the point where there are no warnings in compiler header, in libc++ headers. And this is a hard and ongoing job. People keep adding new compiler warnings all the time. Some of them are really, really important. Some of them are, in my opinion, bogus. Clang recently added a set of warnings that were when you if you assign a literal value to another numeric type, like 187,000 whatever or 187 million something to a float, it will give you a warning and say this value has changed. because that cannot be represented exactly in a float. And this is really nice. I mean, that's an important warning to know. But we still have to deal with those. Sometimes there are some compilers that warn on what I consider just silly, silly things. We had a bug report that if you call make unique of char and pass it 0, there are compilers out there that will warn on this, that you are assigning an integer value, 0, to a char, and this is a possible loss of data. There's not a lot we can do with that. Anyway, so this is always a balancing act, trying to find out, occasionally we have to suppress warnings, but the goal is to deal with as many as we can. And so, and not a lot else to say about that. Let's talk about precondition checking. So many library calls have preconditions. And for a while, we had contracts in C++20, and now we don't. But we have some debug mode in libc++ that will check some preconditions, but not all of them, because some of them are very expensive, or some of them are impossible to check. And we just have to, it's a good way to put it, we just have to depend on the user to get things right. In general, the standard says that if you do not satisfy the preconditions of a library call, the result is undefined behavior. And you never know what's going to happen with undefined behavior. We have, in libc++, we have a macro called libc Assert, which does nothing. You can define it yourself to do interesting things. If you want, and you will get errors if you fail to provide, satisfy the precondition in some cases. This is not as useful as it used to be, or as you might think, because one of the things that people like to do is they would like to define this to throw an exception. Just throw some exception, precondition failure, when the preconditions are not set, not satisfied, excuse me. And that's a problem, because if you're inside a member function or a function which is marked no except, that's just a hard compile error, and you can't do anything about that. So you have to do something else. But let me give you some examples. Vector front returns a reference to the first element of the vector, has a precondition that says the vector cannot be empty, i.e. there has to be a first element. So we have a libc++ assert says not, Lib Cpp Assert says not empty. And this will get, this will do whatever you define it to do. Okay? This one's nice because it's easy to check, it's cheap to check, and it's easy to catch. Sort. Sort takes a comparison predicate that you use to compare. It's used to compare the elements of the sequence to determine how to put them in the right order. Okay, this requires comparison show induce a strict weak ordering on the values in this sequence. Now, the important thing to note here is it doesn't have to create a strict weak ordering for all possible values of whatever the type is that you're sorting. It just has to do it for the actual values that you're sorting. An example of that is if you're sorting a vector, say, of floating point numbers, operator less than works just fine as long as there are no nans in your sequence. But anyway, to get back to this requirements clause, this is something that can be checked. Okay, what are the three things about a strict weak ordering? Reflexivity, symmetry, and transitivity. You can check that. You can check for every value in the sequence is comp AA false. Sure, okay, you can do that. Symmetry. for every pair of values in the sequence, if comp AB is false or is true, then comp BA must be false. There's no way that it can be true for both of them. And okay, now that's an n squared operation. Ooh, ouch. This is supposed to be an n log n sort. That's already much more expensive than the actual sorting, and it's worse because the third one, the transitivity, you checking triples. If comp AB is true and comp BC is true, then comp AC has to be true, and that's an n cubed operation. So we can check. We don't actually do those checks in Lib C++ because they would be so much more expensive than the actual sorting. This one's worse. Stud distance tells you how far from two iterators are apart. Has a requirement that last shall be reachable from first. You can take first and you increment it, and eventually you get to last. How do you check that? How do you actually check that? You increment first. Am I at last yet? Am I at last yet? Am I at last yet? Am I there yet? Am I there yet? Am I there? And I sound like a 4-year-old in the back of a car, right? Is that even the thing here? I mean, it's an old joke in the US, is that people go on car trips and the little kids say, "Are we there yet? Are we there yet? We haven't even gotten out of the driveway. We're not there yet. Are we there yet? Are we there yet?" And if you're not there yet, does that mean it's not reachable? No, it just could be way down the road. You can't check this, okay? There's no way of going and going and going and saying, okay, I've gone far enough. It's not there. So this is an example. So I got 3 examples. We have cheap, which we do. We have expensive, which we usually don't do. And we have impossible, which we don't do at all. Yes, hand here. So the comment was that he said, I know that iterators in general, after you get to end, come back to the beginning. No, you're incorrect. Incrementing an iterator past the end of a sequence, the end iterator of say a container, is undefined behavior. It might get back to the end. It might cause your computer to explode. It might give you a segment violation. It might do all sorts of things. So no, you can't do that. You can check if there are cycles in an iterator sequence, but there shouldn't be. There's a famous interview question about that. How do you check to see if a linked list has a cycle in it? But all that finding a cycle in it means that it's not reachable from first. But that's not a sufficient thing. Anyway, okay, onwards. Static analysis. Static analysis is the ability to basically analyze the source code of your program, build up a model for symbolic execution, and then analyze the workings of your program. There are several of them out there. I'm not really happy with any of them. I have tried Clockwork and Coverity and Fortify. They tend to be very noisy. They tend to report a lot of things which are what I consider false positives. In cases where, for example, we go back to something like this, they will report that vector front might actually access the first element of an empty array. But that's a precondition violation. That's not supposed to ever happen. And so they tend to be very noisy. They tend to give you lots of, like I said, what I consider false positives. I'm still looking for a static analysis program that I would be happy to use, that I could get a lot of value out, but I haven't found one yet. I would really like to find one. The Clang static analyzer I had high hopes for a few years ago but it is not progressing as quickly as I'd hoped. So if anybody here knows about a good static analyzer, I would sure like to hear about one. Okay, dynamic analysis. Dynamic analysis is the idea that you instrument your program at runtime and you run it, like say, run your test suite or so on under this dynamic analysis system and watch for misbehaviors. For many, many years, the preeminent dynamic analysis tool was Valgrind. Some people use Valgrind with great results, but a lot of people did not use it because it had a very serious performance overhead and memory overhead. We don't use Valgrind very much, but instead we use various of the Sanitizer programs that have come out of the LVM project. How many people saw my lightning talk last night? A few. I was first up, and attendance suffered a little bit from the party running over. That's fine. I was talking about address sanitizer. There are many sanitizers now, but basically the idea is you build your program with a sanitizer, with one or more sanitizers, and then you test it. And the sanitizers will report misbehaviors of your program. Address sanitizer, for example, checks for out-of-bounds reads and writes, running off the end of an array, say, or the beginning of an array. Undefined behavior sanitizers, UBSAN, looks for instances of undefined behavior in your code. TSAN, thread sanitizer, looks for race conditions. MSAN looks for memory access violations, things like reading from uninitialized memory. And value sanitizer is brand new, just has landed in the last couple months. And it looks for, it does a very specific thing. It looks for assignments from integral or floating point types to other integral and floating point types where the destination type is smaller than the source type and the value changes. So if you have an integer containing 12 and you assign it to a character, value sanitizer says, I'm fine with that. That's fine. Because the character holds 12. Everything's fine. But if you have an integer holding 500 and you assign that to the character, value sanitizer will say, whoa, 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 whoa. You had a 500 over here and you assigned it over here and now you have a negative 120 or whatever the right value is. And that's a value change. And it's like, nope. And you can quiet this down. This is for implicit conversions. If they're explicit conversions, if you do a static cast, you've just told the compiler, okay, it's okay, I know what I'm doing. Value sanitizer found a couple bugs in libc++. We started using address sanitizer when it was brand new. If you look at the dates on these blog posts, 2013, that's 6.5 years ago. It found 6 or 7 bugs in libc++, and it found a couple, 3 bugs in the libc++ test suite when we started running these. There was one, it was a heap corruption bug. We had a case in libc++ where in one of the IO streams, where if you went through a very specific set of operations, it would allocate a buffer of 0 bytes, and then would resize it as needed to accommodate when you wrote into this buffer. But there was a case where it would write 1 byte and then resize it. Write 1 byte into a 0 byte buffer. And that's a buffer overflow on the heap. It turns out that on macOS, this was completely harmless because the memory allocator on macOS always allocates a multiple of 16 bytes. So even when you ask for 0, you get 16. Now, that being said, it's still a bug. Can't really depend on that behavior of the macOS memory allocator, and libc++ absolutely runs on other systems other than macOS. So it's something that had to be fixed. So I was very, very happy to see this, because if somebody here reported that to me, we get this occasional heap corruption on, this Linux system. I've tried to reproduce it on macOS and gone nowhere and nowhere, and we'd gone back and forth a bunch of times. Anyway, so that was a great thing to find. There were a couple others, but that was the main one. And it was, it's really great. Address Sanitizer, I cannot recommend it highly enough. It's like you can use it, you build your programs with Address Sanitizer and run your tests on it and see if it misbehaves. The nice thing about Address Sanitizer is it only goes off when something goes wrong. There's really no false positives for Address Sanitizer. It's like, you've read off the end of this array. You've written off the end of this array. You've written this random byte out here in your global space. Things like that. And it tells you, here's a stack trace, here's where the write went. Here's how you got to where you wrote things wrong. It's a wonderful tool. UBSAN does checks for various flavors of undefined behavior. It's very nice. I have given talks about undefined behavior in the past. You can find them on YouTube. Undefined behavior is very hard to eradicate from your programs, but it's well worth doing. UBSAN is a great tool for that. It's an ongoing, working with UBSAN is an ongoing thing, because Richard Smith, the person who's the author of UBSAN, keeps enhancing it to find additional kinds of undefined behavior. Okay. Fuzzing. Let's talk about fuzzing. How many people here are familiar with fuzzing? Oh, more than I thought. That's great. For the about 60% who did not put their hands up, the idea behind fuzzing is that you take random inputs and you give them to the program under test, and you watch for misbehaviors. Address Sanitizer is a great tool with fuzzing, because Address Sanitizer will take hard to reproduce failures and turn them into immediately reproducible failures. But anyway, modern fuzzers like OSS Fuzz and American Fuzzy Lop do profile-guided fuzzing, which means that they will generate random inputs and give them to your program under test over and over again, and then while they're doing this, they gather performance coverage, code coverage metrics from the code that is being tested, and use that to influence how they generate the next random input. And what happens is, over a period of time, they will basically explore the entire execution space of the code under test. This is very, very handy. Okay, so people who know about OSS or about fuzzing, how many people know about OSS Fuzz? Much smaller number, a couple. OSS Fuzz is a tool that is being run by Google, actually. Stands for open source fuzzing, and it is basically fuzzing as a service. You register your open source project with OSS Fuzz and give them a link to your GitHub repo and say, this is how I want you to fuzz my open source project. And they will pull your code from your repo and build it. And on Google's compute cloud, they will fuzz it. And then they will report bugs against your code based on what they've found in the fuzzing. And this is great. And they report them, basically, they report them privately and say, look, in 90 days, we're going to make these public. So you should fix these. But OSS Fuzz, here's a link. If you want to get into fuzzing, this is a very nice way to set up this ongoing fuzzing infrastructure. All right. This is also another place where people who want to get involved in libc++ would be quite welcome. Anyway, let me give you an example of fuzzing. I wonder why there's a 4 on the title of this slide. I don't know. Anyway, so here's a fuzzing target for std partition. Okay? The fuzzing infrastructure passes us basically a pointer of UN8Ts and a size. Okay? That's the data to be input. And it is up to the person writing the fuzzing target, me in this case, to determine how to use this. Okay? And so this one for partition is actually fairly straightforward. I make a copy of the data in a vector. I call partition on the vector, working.begin, working.end, with a predicate which is called is even. I suspect you can all actually figure out what is even does. Okay. And we have address sanitizer and UB sanitizer enabled, so we're watching for misbehaviors, see if any out of bound reads or writes, or anything like that, or any undefined behavior, and we'll assume that there isn't any, and that the program does not crash. So, all right, partition returns, and we say, okay, it returned. How do we know it's successful? So what does partition do? I feel like Sean up here. What does partition do? It splits the sequence into two halves, where the first half is all the things that satisfy the predicate, and the second half is all the things that don't. And by half, I don't mean exactly 50%. I mean there's all the ones that do, and then all the ones that don't. So it might be 70-30, it might be 100-0, what might be 199. But anyway, so what do? We test. We say if we expect that all of the ones from the beginning up to the partition point, which is returned by partition, all the ones that are from the beginning up to the partition point, half open range, remember, satisfy the predicate. And none of the ones from the partition point to the end satisfy the predicate. Now, yay for half open ranges, and yay for all of and any of and none of dealing well with empty ranges, because I don't have a special case any of these. So that's the that is the post condition for partition, is it leaves the sequence in this state. But there's an additional post condition here, and that is, do we have the same set of values that we started with? Is there a bug where when partition is moving things around that it overwrites something or duplicates something? And so I have another one called is permutation. I say is the things in working, is it a permutation of the original data? Because I haven't touched the original data, remember, because it was A, it's a constant, and B, I made a copy of it. Is this a permutation of the original data? And yes, I should be using the four parameter iterator version of is permutation, but that wouldn't fit on the slide. So I didn't. Anyway, so is permutation, data plus size, working.c begin, and there should be a working.c end on there, but like I said. And then otherwise return 0. Returning 0 in this case is success, that everything is fine. And we have tests for fuzzing tests for all the sortings and the searching and the heap operations and all the regex stuff. And again, I consider this to be very much a good start. There's a lot more that could be done here, but I don't have much time, which is why I said if anybody wants to get involved, I'd be happy to talk to them about it. Okay. And I did roar right through all that, sorry. Questions now?
We have plenty of time for questions. Please raise your hand if you have a question for Marshall.
Down in front.
Thank you for the great talk. Question is regarding fuzzing of the regex.
Mm-hmm.
Are you generating random regex, or let's say random strings that are used for regex, or are you actually only generating the correct regex syntax and testing it semantically, not just syntax of a regex?
So no, I'm using the inputs as a regex, because one of the things I wanted to do was I wanted to make sure that my regex parser did not crash on bad inputs, things that were not valid regexes. So actually what I do is very simple. I take the input data here and say, make a regex from that data, and then try to match it against itself. I mean, there's quite probably a better way to test regexes, but that does work. And it found 4 or 5 really annoying bugs fairly quickly. And now it's finding all sorts of things that, well, regexes are basically a Turing-complete language. You can do all sorts of things with regexes, and so now I'm down to trying to fix stack overflows and things that regexes that take up 2 or 3 gigabytes of RAM to process, because some people send me, the OSS bug reports, they send me reduced regexes which are 750K bytes, and it's just like,
Thanks.
1, 2.
Yeah, thanks for the great talk.
Thank you.
I have the question about the beginning of your talk about testing a large, testing fat tests, large tests. You don't run them only because of their size? Why don't make them nightly tests?
I'm sorry, I missed a word out of it. Yeah, I don't do what?
In Lib C++, you don't run large tests like n-cube complexity only because of their complexity?
That would be the precondition violations.
Yes.
I'm sorry, I went to the wrong place. I thought you were asking about testing. Yeah, yeah. We don't do this precondition because they would be significantly more expensive than the actual sorting algorithm.
But why don't run them from time to time?
We run. All we really do when we test the precondition checking is we verify. We define in our test suite. We define Lib Cpp Assert to do something that we then detect in the test to say, oh yeah, it caught this. It caught this. We could actually do that for these expensive ones, but I don't think that would serve our users well. I mean, we could do it for little sequences in our test suite. That'd be fine. But I'm just saying the test itself, I don't think would serve our users well when they enabled it, because they're going to want to test it with non-trivial amounts of data, and suddenly their sorting performance would go. That's why.
Thanks.
There was somebody, yeah.
Thank you for the talk.
Thank you.
Can one test a container with a fuzzing technique?
Can one test a container with a fuzzing technique? I'm sure you can. The question is, a container is actually a whole bunch of calls, and so really, when you're fuzzing something, you want to think about testing an individual call. You could argue that I am testing, the pointer and length constructor of vector right here, but I'm not. I'm just assuming that it works. But I could certainly set up a fuzz target for that particular constructor on vector and test and make sure it works. I just don't think that's worth doing. But there are a bunch of them that there may be. Set, for example, set insert would be interesting, because it's quite possible that some of the test cases that are randomly generated contain duplicates, and you want to make sure that there's no memory leaks when you're trying to insert a sequence that contain duplicates, or duplicates that might already be there, things that might already be there. That would be an interesting thing to test. So no, I don't think testing container with fuzzing, but testing individual calls in a container would be a good thing to do. Thanks. Somebody over here? And then somebody in the back, too. Yeah.
Marshall, thanks a lot for the presentation and for the
Thank
fact
you.
that it's very easy to understand. Talking about ASAN, it's a great tool actually, and performance-wise, it's much better than Valgrind. But still, did you have some cases in your practice when it was bad for the performance, when you couldn't use it because it's imposed too much penalty on the performance?
So I did not actually run into cases where ASAN was an intolerable burden, a performance burden or memory burden. In my tests, and I wrote these up, like I said, quite a while ago, but in my experience, ASAN adds about a 20% performance penalty. So at the time I was running my the libc++ tests on a laptop. It wasn't this laptop, it was one before this, but it doesn't matter. And it took about 20 minutes without ASAN and about 25 minutes with ASAN. I noticed that the tests in general used more memory, sometimes even twice as much memory. But since all the libc++ tests tend to be very small programs, this was not an issue for me. That doesn't mean it's not an issue, just not an issue for me. Yes, ASAN, all of the sanitizers involve overhead. Some of them, like TSAN, can actually have a fairly high runtime overhead in terms of performance, and ASAN can sometimes double your memory usage, and especially in the days when we were using 32-bit machines and people were pushing up against 4 gigs of RAM is all you had. That was a big problem. At the moment, I believe memory is fairly cheap and expansive. We have lots of address space at the moment. That won't last. Programs will continue to grow and data sets will continue to grow, and we'll be, in a few years, we'll be back at the place where there are systems which are very tight on RAM. So I did not find that the performance or memory overhead for ASAN was excessive. Your mileage may vary. You may be in a tight memory situation. I see 3 hands.
Thank you for your talk. Yeah.
Thank you.
I have a question about Thread Sanitizer. Do you use it?
Thread Sanitizer?
Yeah.
We currently do not have a bot that's running Thread Sanitizer. And part of that is because, not for any good reason. Sorry. Not for any good reason. Thank you. I will go and talk to people about getting one set up, because we should make sure there are no race conditions inside the threading infrastructure in libc++.
And what about Leak Sanitizer and about that?
I am not familiar with Leak Sanitizer, so you've given me something else to look at.
Okay, yeah, another question I would like to ask is, do you use Pragma system header, or what do you use to, it's about warning and errors. You say that you try really hard to not to give any warnings or errors in the modern compilers. When people use your libc++ library, yeah, as far as I know, in libstd C++, they don't care that much about warning and errors. And if, for example, I compile something, just include vector, and I pass -w system headers, that's like 20 pages of errors, even if I include vector and some simple examples.
So we do use Pragma system header. We use it. It's pretty much a necessity for writing a standard library, because some of the things, for example, the string literal suffixes, like %s, not %s, but quote s for strings and so on, they're reserved for implementations. Now everybody else has to use double quote underscore S or something like that. And so the only way the compiler knows this is it knows it's in a system header. And yes, we do build every now and then with, when I run the test suites, I try to turn off the suppression of warnings in system headers and see what happens. So I'm aware that sometimes, that some of those warnings get suppressed, but it's also there are some facilities that are only available to system headers, some facilities in the compiler, and so that's why we have to do that.
Thank you. And the last question, I think, how do you test against different architectures? So what is your test suite running? What does it actually do? What does actually happen when your bot or something asks to run the test? Which machine do they run on? Is it Docker, or what kind of technologies do you use beneath that? So because libc++ should work on every major platform, every major architecture, and there are a lot of them. So yeah, if you have something like Stud Atomic or something like that, you should check it in different circumstances. And
I am fortunate enough that there are people who are very interested in libc++ who have contributed hardware to run the tests, and so we have various pieces of hardware around the world that run libc++ tests. I do not actually have any specialized hardware in my office to run the libc++ test suites. All I have is pretty much x86. But I get reports from the bots when I check something in which breaks something on PowerPC or on ARM or on some weird machine that IBM Canada runs, or so on and so forth. So we get tested on lots of different hardware. We don't actually use Docker for those kind of things. We just, you have a machine. We use the BuildBot testing infrastructure, and we just compile them and run them.
Okay, and as you mentioned that you tried to turn off systems headers, if I use libc++, I also can turn them off and try to.
Right.
So there should be not a lot of bugs. Yeah.
There should not be a lot of bugs. There will be things that don't compile, because if you turn off system headers, the things in the string literals or the chrono literals, the compiler will just reject them out of hand. But hopefully there are not a lot of warnings.
Okay, thank you.
Thanks so much for your talk. Actually, my initial question was about threading, but okay, I will ask another one. Currently, we have C++20 coming in, but in C++14, there were two functions added, toChars and fromchars. What about their status in libc++ library, especially regarding floating type support?
So C++, toChars and fromchars that were introduced in C++17. There is a person an old friend of mine who is working on these implementations. They're not yet ready. These have turned out to be quite difficult to implement. I mean, have you watched Stefan's presentation from CPPCon last month? These are quite difficult to implement, much more difficult than anybody thought. And so he is working on these, and I believe he's making good progress, because I keep getting emails from him with questions, but they're not currently implemented.
Thank you much. We are waiting them.
Actually, let me rephrase that. They're currently implemented for integral types, not for floating point.
Are there any good techniques in libc++ that have been taken from or influenced by Microsoft implementation of the library, or any other?
Any things that have been taken out of libc++ and used in other standard library implementations? I'm sure there are. I'm just not thinking of any at the moment. the number of standard library implementers in the world is actually fairly small, and we tend to talk. And so when somebody finds a good way to do something, they tend to tell the other implementers. And if you can adopt them, you do. Because if you say, yeah, that's better. For example, in a very minor way, I did a bunch of work with STD midpoint, which is a very small call that was added for C++20. And I kept sending emails to Jonathan Wakely and to Stefan at Microsoft as I found things out. Hey, this doesn't work, and this doesn't work, and this does work, and so on and so forth. And it would not surprise me if they took, took a bunch of stuff from the emails I sent them. We also send tips to each other and report bugs against each other's libraries on a regular basis. It's, like I said, it's not a big community. And so we tend to share implementation details. Now, obviously, given that libstud C++ is GPL v3, I can't go lift code out of their repo and paste it in. But if Jonathan tells me how he did it before he checks it in, it's not covered by the GPL, and I can use it. Microsoft has recently open sourced their standard library, and it's now under a permissive license, so I could go and get things from there. They have always been able to get things from my library, and I have sent from lib C++, and I have sent suggestions to them.
Thank you.
Mm-hmm.
Does the community of the implementers of the library use only email for communication or any other modern technique?
Oh, no, we use all sorts of things. I'll see them all on Monday, for example, at the standards meeting. But some of them I talk to on Slack, some of them I talk to on IRC, sometimes we do emails, sometimes we exchange things in various Bugzilla instances. There's all sorts of ways to talk.
Hello, thank you for the good work.
Thank
you. I have a question about multi-threading. All these tests are about memory or some static analyzing. How do you test, which tests do you have about concurrency primitives? For example, mutex, atomic primitives, or something like that?
How do we test things like mutexes and atomic primitives? Not near as well as I'd like. We test them, we test and we lock a mutex, and then we try to lock it again and see if it fails. We call try lock, for example, and make sure it fails. Or we do timed waits and make sure we wait at least that long. I would love to have a better way to test those. I don't know any great ways to test them. So.
As your opinion, what do you think is the best practice for tests like that, for concurrency primitives tests from your
for testing yes. Atomic primitives?
All tests in for concurrency primitives. For example, if you write some primitive thread safe object, which test should we do for this primitive?
Okay, I heard you say iterator primitive and list primitives. Is that right?
Yes.
Okay. Well, I mean, those are actually easier than the atomic primitives, but part of it is because I have a unique advantage. At least in all my experience in the industry, this is the first project I've worked on that has a stable, accurate written spec. Okay? Not very many projects actually have that. And so I can say, I can look at an individual call in the standard and I can see exactly what it's supposed to do, what parameters it's supposed to take, and what it's supposed to do. And basically, I just write tests from the standard. This one, I would say, I would write a test that verified that I can call it with 2 iterators, that it returned the correct type, the difference type of the iterator, and then I'd set up some sample iterators that I knew the distance from, whether they be input or random access and so on. I have a large set of iterator facades, basically, fake iterators, and then that I know the answer, then call distance and say, this should return 3. Does it return 3? And so on. And same for no except, as I talked about earlier with clear. Things that should be no except, verify they're marked no except. I don't have to worry about testing whether or not they actually throw things, because if they actually threw something, the test would fail, would call terminate.